Ladies and gentlemen, class recording has begun. So. Next thing that we come up. Yeah, good. Yeah, here we go. 2014, yeah. Next chapter that we come across in your book is chapter 6. Chapter 6 deals with work and energy. We are still dealing with mechanics. We are still looking at motion. And we are looking at the same kinds of motion. There will be things speeding up. There will be things slowing down. There will be things going upwards and downwards. Things that we've talked about over the past couple of units. But we're going to look at them from a little bit different perspective and analyze them a little bit differently. It's not a different kind of problem. It's a different way of looking at problems. Just another way of trying to explain what's happening and why it's happening. That's really where we're headed in this chapter. The focus of chapter 6 is on work and energy, so we have to define a couple of terms first. The packet that I gave you deals with work, but before we get into that, I wanted to give you a couple of definitions. First, energy. We use energy to explain a bunch of things, both in the big macroscopic world, that being, things like airplanes and cars and basketballs and stuff like that. And we use energy to explain what's going on with those things. But we also use energy to explain things like atoms and molecules and stuff like that. In its most general form, we look at energy as the ability to cause a change in matter or the environment. Energy changes things, or can change things, cause things to be different than they were before. We've sort of dealt with that concept before. We've dealt with a quote-unquote change concept. What term have we sort of used to represent the change in an object up until now? Acceleration, right? Acceleration is the change in the movement of an object, or the change in the velocity of an object. So we will definitely use acceleration as a way to help us explain energy, or use energy as a way to explain acceleration. Like I said, it's not new kinds of problems, it's just explaining the problems we've done a little differently. That being the case, we also deal with the concept of work. Work is the transfer of energy between objects. Moving that ability to change stuff from one object to another object. And like it says underneath, right, the energy of an object will change when work is done. So this concept of work deals with changing the energy of an object, changing its ability to cause a change in something else. It has more or less ability to do stuff. Stuff being, of course, a general term. Right? What that stuff is depends on what we're talking about. But when we talk about work and energy, we're talking about the ability to change things, and then increasing that ability, decreasing that ability. That's what those two terms are in their most general form. All right, good there? Now let's get to the packet itself. So the first thing we talk about in chapter 6 is work. And, Margo, we kind of said before that energy is sort of related to acceleration, right? The change in an object. Last chapter, we talked about acceleration and it being affected by two things, right? Do you remember what affects the acceleration of an object?
Yeah, inertia.
Inertia, which gets measured by what? What tells us about the inertia of an object? Anybody?
Frictional force.
Mass, right? Remember we talked about inertia as mass. So mass can affect acceleration. What else can affect acceleration? What? Acceleration is a change in velocity. What causes that change, though? Somebody else can jump in on this. He doesn't have the answers. What do we say? What affects the acceleration of an object? It's mass and
force.
this equation right here, right? Sigma F equals m times a. Oh yeah, put the equations up.
Ah.
Yeah, so good tape.
Yeah, got it, yeah. myself some painter's tape. So. But we talked about the idea that acceleration is caused by force, but then also affected by the mass of that object. So when we talk about work being a change in energy, right? Work is going to also depend on force, but it also depends on distance. Okay? When we talk about changing the energy of an object, we have to have a force that's acting on that object. But force isn't the only thing that's involved. For example, if I take that ball, right, sitting there, if I want to make it move, what do I have to do to it? Push it, or apply a force, right? I could apply a very large force. But one thing that the last chapter doesn't explain very well is that the amount of force is really only one factor that goes into determining what ultimately happens to this ball. For example, okay? Don't worry, strong. So, I applied a force to that ball. And, all right, it was a relatively large force, okay? But how long did I apply that force? Like a split second, right? And ultimately, the change in that object wasn't very much, right? It started rolling along the table, but it really wasn't rolling all that fast, okay? If I take another force that, if we actually measured it, might be a little bit less than me flicking the ball with my finger, right? Like this. Okay. In that case there, the force I applied might not have been as much. But because I applied the force starting way back here and ending way over here, right? What did we ultimately see about the change in that object? More or less than me just flicking it real fast. Changed a lot more, right? Fly across the room, right? Maybe destroy something over there, whatever, you know. So. But it's not just the change that an object experiences isn't only dependent on the force. It also depends on, okay, well, what do we do with that force? How long are we applying it? How far do we apply it? All of those things will go into the ultimate change an object experiences. Key point. How do I know? It's got a key, right? In the simplest case, work is done when a force is applied to an object and the object moves in the direction of the applied force. That's what we call work. We apply a force, and that object moves because of it.
So that means, like, if I push that desk,
Yep.
I don't move it. I didn't do any work to it.
Did not do any work to it. This is another one of those situations in the last chapter too, where we talk about terms that you know what work means, and you know what energy means. But here, they have specific definitions. And if we don't understand those specific definitions as they relate to these ideas, we might get confused as far as answering a question, right? Yeah, so there's two requirements in order for work to be done. We have to apply a force, and that object has to move because of it. If I push and push and push on this wall all day long, I would be, quote unquote, working hard, but in the physics standpoint, no work. Hardly working, exactly. So, all right, good there? So, Alex, just to kind of illustrate that point a little bit more, right? Here, you guys have this picture on your sheet there, right? This guy applies a force to the box moves because of the force. This is work. If this box had a lot of mass, there was something really, really heavy in it, and it didn't move because of his force, right? He pushes it really hard, but it doesn't go anywhere. That's not work. The energy of that object would not change. It's not any different than it was before he applied the force. And that's really the key. Is the object different than it was before. It doesn't physically have to change. It can just change where it is or what it's doing, but is it different than it was before? Here, over on the side, just to kind of make sure that we're putting stuff together, ideas like force, mass, acceleration, these things are all going to be important in this chapter. Even though we introduced them in the last chapter, we will use them again in this chapter to explain things. So they're going to come up again, right? We're going to keep reinforcing those concepts. What does it mean here? What does it mean there? Good there? We measure work in a unit called the joule because work depends on force and distance, right? Work equals F times D.
Rhymes with cool.
It does rhyme with cool. There it is. It's totally uncool that they said that, but it does. Think of more things that are uncool. We'll show you in a second, right? Force, distance, right? Force measured in newtons, distance measured in meters. So the unit, when we calculate the work, would be newtons times meters. You just mash them together. But that combination we call a joule. So joule is equal to newtons times meters. But in the previous unit, we talked about that newtons actually is a combination of some other units. So if we plug that in, joule actually represents this combination of base units. Kilograms times meters squared over seconds squared. So we got a big conglomeration of units that is all represented by the letter J. That will be important when we go a little bit later on and we talk about how much work an object, or how much work is done on an object and how fast does it end up going, blah, 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 blah. Speaking of being uncool, Sam, if you want to have a unit named after you, you might have to conduct physics experiments while on your honeymoon. Okay? Just saying, right? You got to make a choice. Honeymoon or having a unit named after you. Right? Pros, cons. You know, make yourself a little pros, cons list, then you decide. Right?
That's not something to brag about.
I'm just saying. I'm not bragging. I'm just saying. If you want a unit named after you, right, the busser, you might have to make some sacrifices. That's all I'm saying. All right. It might involve conducting physics experiments while on your honeymoon. I don't know.
I mean, back then, how exciting was a honeymoon? Like, where did they go on
Hey,
their honeymoon?
I don't know, but
It was still a honeymoon.
it was still a honeymoon, right? I don't know if a trip to Tahiti was in the cards then. I don't know, but whatever. All right. Real simple, straightforward calculation here, okay? Intern pushes a 72 kilogram patient on a 15 kilogram gurney, producing an acceleration of 0.6 meters per second squared. How much work does the intern do by pushing the patient in the gurney through a distance of 2.5 meters? First things first, what is this problem asking us for? Work, right? How much work? One of the things that somebody else brought up earlier, in the last unit, we talked about the idea of weight. Weight being the force of gravity. And I said sometimes in this book, they will use the letter W to represent weight. And I told you that I didn't like that, right? And I usually use this, right? F of G, where to illustrate that weight really is a force that comes from gravity. This is another reason why I don't like using W for weight, because now we have another W word. So to try and keep them straight, we'll keep W to mean work, and when we talk about the weight of an object, we'll do F of G. We just talked about that the work done on an object depends on two things, right? What are the two things that the work depends on?
Force and distance.
Force and distance, okay? Force and then distance. And if we're going to calculate the work, we need to know those two things. Do we know either of them right now? Okay? Distance of 2.5 meters. So that means that this intern pushes the gurney 2.5 meters down the hallway, which isn't very far, but whatever. Do we know the force? force? Did it give us a Newton's value in here? It didn't, but it did give us some other information, right? First, it told us that this object was accelerating. Right? And Margot, we talked about earlier, right, that if acceleration is occurring, what does that mean? There has to be what? There has to be force. And it also told us about this object that she is accelerating. It's a patient, but it's a patient on the gurney. She has to move both of them. So let's take those two masses, add them together, and get a mass of 87 kilograms. Good there? Like we just talked about in the previous screen, or 2 screens ago, I guess. These ideas of force, mass, and acceleration still apply when we talk about work and energy. So let's draw ourselves a free body diagram to represent or to help us analyze this situation. Forces. Right? We got this force here. That's her pushing, right? What do we usually label that one as? Right? For applied force, yes. Okay. That's her pushing the gurney along the hallway. What other forces can we put on here? Let's put F of G, right? Okay. Gravity's going this way. And what else? Normal force, right? Margo, how big is normal force going to be in this problem? How do you know that? Just a good guess?
Oh, yeah.
Which way is this gurney moving?
This way, no.
To the right, right? It's moving horizontally,
Yeah,
but
it's not going up.
it's not moving up or down, right? So those two forces have to balance. While they didn't give us what the force was, we do know from the last chapter that net force is equal to mass times acceleration. How many forces are there on this gurney? 3. But what do we know about 2 of them? They're canceling each other out, right? So when we talk about sigma F now, we really only have to worry about the one force that we want to know, right? So that goes there. And then we said that the mass of this object is 87 kilograms. The acceleration is 0.60 meters per second squared. So we can figure out how much force this intern is applying to the gurney. If I remember right, it's 52.2? Is that what it is? But is that what we want to know? They asked us how much work was done. We just learned that work is equal to F times D. Right? Force applied times the distance. We know the force now. It's 52.2 newtons. And they told us that the distance that this force was being applied, 2.5 meters. So now we can figure out how much work was done. If I remember correctly, anybody have their calculator out?
Yeah.
Is that what it is? Units wise, right, we have a newtons here, we have a meters here, so newtons times meters, right? Okay. We know that the unit's going to be joules. If we go back to our problem, right? 2 sig digs, 2 sig digs, 2 sig digs, 2 sig digs, right? So probably should round this answer to 130. Good there.
Does it matter if it's an uppercase J or lowercase J?
Yes, it does. It's a capital J.
Oh,
So,
it is a capital?
yes. So yeah, make it a capital J, if you would please. All right, good there? Okay. Next picture, which is on your next page. Picture of a guy pulling his suitcase through the airport, going to somewhere between Date 29 and 37 from this picture right here. Okay? Is a force being applied to that suitcase?
Yeah.
Yeah. Is it moving? Yes. So is there work being done? Yes. Is it different than it was before? It was sitting still, now it's moving, yeah, it's different. It has a different amount of energy. But, as you can see here from the picture, right, this blue arrow represents the distance, how far it moves down the hallway or down the concourse of the airport. But, if we look at the force,
Oh, wow.
it's on recording now too, so. That force is being applied in this direction at an angle. Is the force exactly in the direction of the movement? Not exactly, right? It's moving horizontally, but this force isn't being applied horizontally. If we have forces that are at angles, not being applied horizontally or vertically, what have we been doing with those forces? Finding components, right? This force has a component, or two components, right? It has a horizontal component, and then it has a vertical component, right? The applied force along the x-axis, and then the applied force along the y-axis. Which is the important one in terms of analyzing the work that's being done in this picture? X, right? Because that's the one that's actually causing the object to change. If we look at this triangle, right, this being our angle here, what side of the triangle is the x component? The adjacent side. So which trig function could we use to figure out that side? Cosine. What they've done here to illustrate another key point. How do I know it's a key point? It's got a key. Right? Only the component of the force in the direction of the displacement does work. So while this guy is applying a force to the suitcase, not all of his force is going to doing work. What that does is it changes our formula for work now to look like this. Instead of just FD, it's FD cosine of theta. By throwing the cosine into this equation, we are automatically finding this component, or the horizontal component. By including the cosine into the formula, into the equation, we are automatically getting that horizontal component, and that's the one that does the work. Right? And that's important when we have force and distance that aren't in the same direction. Okay? Good there. We'll stop there for today. We'll pick it up from there tomorrow. Okay?